I'd like to welcome Dr. Gopala, Anumachipalli, and Dr. Laura Gwilliams. Gopala is the Robert E. and Beverly A. Brooks Assistant Professor in the EECS department at UC Berkeley, where he leads the Berkeley Speech Group. His group focuses on the science and engineering of spoken language with application to human health, both for screening speech disorders and externally restoring lost function using brain-computer interface. He obtained his PhD from Carnegie Mellon University and went to UCSF for postdoctoral training with Dr. Edward Chang, where he built the first brain-computer interface to decode intelligible language signals directly from the cortex. Welcome. Dr. Gwilliams is an assistant professor of psychology and by courtesy of linguistics. She's jointly appointed between Stanford Psychology, Tsai Neurosciences Institute, and Stanford Data Science. Her work is focused on understanding the neural representations and operations that give rise to speech comprehension in the human brain. To do so, she brings together insight from neuroscience, linguistics, and machine learning, and takes advantage of recording techniques that operate at distinct spatial scales, MEG, ECOG, and neuropixels. Welcome, Dr. Gwilliams. So they will each come and present and then take questions as a panel. Thank you. So Dr. Gwilliams will be talking about receptive language and Dr. Gopal about expressive. So I thought that she should go first. Thank you.
Thank you. Hi, everybody. Thank you so much for being here. Thank you to the Synchrony organizers for putting on such a great conference and for giving me the opportunity to share some of my research with you today. So my work is focused on understanding this big question of how is it that the brain is able to transform the auditory signal of speech into a conceptual understanding of what it is that's being said. And so I'm focused on, I'm focused on understanding the processing system, the human brain, which is able to so rapidly translate sound into meaning. This does not work, okay. And in order to address that question, my research has a number of important components to it. So one really important aspect is that my work is multidisciplinary. So by that I mean I work between neuroscience, machine learning, and data science, as well as cognitive science. And this is a really important component of understanding how the human brain processes language, because we need to be able to pull all of these different disciplines together in order to provide a meaningful answer. I also work with naturalistic experimental paradigms. So that means that I'm trying to study language processing in a setting that people engage with language on a daily basis. So I'll have my research participants, for example, listen to an audiobook or listen to a podcast while I record their neural activity so that I can understand how their brain is operating as they're actually engaging in tasks or activities that they would choose to do in their everyday life. I'm also a big supporter of open science, and as you'll see in my talk and my work in general, I will release my data for use by the community as well as the code that's used to perform the different analyses. And finally, my work operates at different spatial scales. So today I'm primarily going to be talking about my work using non-invasive whole brain measurements, including magnetoencephalography, which we heard from a little bit earlier, and electroencephalography, as well as invasive methodologies, which I'm going to talk about less today. Okay, so I want to show you some of the results from one of my studies that is the foundation for a project that was recently generously funded by the Brain Foundation. So I'm going to talk today about some results that I obtained in neurotypical adults and was able to develop different analytical methods that now I'm going to move over to the domain of non-speaking autistic individuals. So this work is about decoding different hierarchical properties of speech from the neural signals. So let me explain what I mean by that. So when we hear somebody speak, we hear these fluctuations in air pressure, and that gives rise to the sensation that there is a sound entering our ears. And this sound, when it pertains to speech, contains a hierarchy of different properties. So from the fluctuations in air pressure, we can identify each individual sound that is present in the speech signal. So it's an F or an A or a T or a K. And then those can get assembled to create more and more complex and abstract properties, like the syllables that the person is saying, or the morphemes that somebody is saying, or the words that they're saying, or the sentence structure, and ultimately the meaning that that person is trying to convey. So speech is hierarchically structured in this continuum which goes from sound all the way up to meaning. And so in this work, I wanted to understand, how does the brain create these hierarchical representations that map from sound to meaning? So the idea is that the brain just can't just directly transform sound into meaning, because those two things are only arbitrarily linked. You need to learn the associations in order to be able to understand what someone is saying. And so the critical question is, okay, what are the intermediary representations along this continuum that allow the brain to make the speech sounds become closer and closer to the meaning of what ultimately is being said? Okay. So the way that I address this question of what are the representations the brain's generating during speech processing is by recruiting 21 native English participants. These were neurotypical adults, and they listened to 2 hours of audiobooks while I recorded their brain activity non-invasively using a magnetoencephalography, or MEG device. And this data actually is the most comprehensive of its kind. So I actually have publicly released these data. A number of different groups across the world actually are using these data to address a bunch of different questions. Okay, so we have the 2 hours of stories that these people are listening to, and I annotated those stories for a very comprehensive suite of different properties of language, like what I just described. So I annotated them for 50 features in total, spanning from more sensory sound features all the way up to more meaning level features. We can organize these features into 6 feature families. So we have properties, phonetic properties, which refer to how each individual speech sound is articulated. Properties about the syllables and morphemes that are contained in each word. Properties about the words themselves, like are they determiner, adjective, noun, verb. And then properties about the sentence structure. So, for example, at what points in the sentence can we actually bind words together? So here, for example, we can bind fat and cat to make a new semantic object. And how complicated is the sentence at that moment in time? And then finally, at the top of the hierarchy, we have the meaning of what it is that's being said. And this is where I'm able to take advantage of advances in large language models to numerically summarize the meanings of words and phrases and use this as a proxy for the semantic representations that the brain is ultimately generating. So the idea then is to take the neural responses of the people listening to these 2 hours of stories, along with the annotations of those 2 hours of stories, and see if we can actually reconstruct these different properties of language from the neural activity. The idea being that if we can do that, we can understand which properties of language are actually generated in order to help these people understand the stories they're listening to. And because MEG, the neural recording device I mentioned, is time resolved, it also allows us to address the question of what order are the representations generated. So let me just briefly lay out the hypothesis space there. So one hypothesis says, okay, language is compositional. So you have speech sounds which get combined to make syllables, which get combined to make words, combined to make phrases, combined to make sentences. And so language processing is going to be compositional as well. That means that when we query the brain activity to say what properties are encoded, we'll find that earlier in time, the lower level properties of speech are encoded in the brain activity, like the individual speech sounds. And then gradually later in time, as the representations are more abstract and closer to the meaning, they'll be encoded later in time, because it takes more time in order for the brain to actually create the meaning of what's being said, and less time to create the actual sounds that were said. The alternative hypothesis is that, hang on, these people listening to continuous stories. And so that means that a lot of the time they might actually be able to anticipate or predict the meaning of what they're about to hear before they actually hear it. And if that's the case, we would actually see that the higher order properties, like the semantics, the meaning of what's being said, is actually present in the brain activity before the individual speech sounds are said. So these are the two extremes of the hypothesis space we can test. Okay. So let me show you the results. I'm going to show you the decoding on the right-hand side here. We have time on the x-axis in seconds relative to when each word in the story happened. And I'm going to show you the decoding of each of those 6 feature families. So here's the decoding of the phonetic features. So this is the speech sounds. And this bar here shows you when in time we can read out the speech sounds the person is hearing just based on their brain activity, better than chance. So we can decode the phonetic features from 0 to 200 milliseconds, sublexical features from -200 to 500 milliseconds, word class -200 to 200 milliseconds, syntactic operations -200 to about a second, and the syntactic state and the semantic vectors were decodable from half a second before the word ended until a second and a half afterwards. Okay, so there are a few things that we can take from this result. One is that this very comprehensive set of features that I said span from sound to meaning, all of them are present in the neural activity of these people listening to these audiobooks. And the second thing is we see very interesting dynamics in these responses. So we see that actually the higher order properties of speech, like the meanings of the words and phrases, are present in the neural activity earlier than the lower level properties. And they're also present for a much longer period of time as well. I also like to highlight the degree of parallel processing that we see going on here too. So for quite a long period of time, this entire hierarchy from sound to meaning is all encoded in the brain at the same time. And I think this is precisely what allows the brain to resolve things like ambiguity, because if you can use the meaning of the word to figure out what speech sounds were actually being articulated or vice versa, then this leads to a very robust comprehension system. Okay. So then in terms of the two hypotheses that I laid out, The hypothesis which clearly wins out here is this reverse hierarchical hypothesis, which said that actually the more complicated abstract properties of speech will be available to the brain earlier than the lower level properties. And I just want to give a little bit more intuition as to why I think that's the case. So what I think is happening here is that the higher order structure, like the meaning of what's being said, is built based on the context of what has been heard before. And this context serves to make educated guesses about the information which is going to be presented at the lower levels. And then once the sensory information is actually received, this can be used to then be integrated with those predictions. So integrated with the predictions if the predictions were correct, or updated if those predictions were incorrect. And finally, as I said, there's a high degree of parallel processing, which I think allows the system to be robust against noise and ambiguity. And critically, all this reverse process is only possible because the individuals are able to predict what is about to happen. Okay. So to summarize, in this study, we found that these non-invasive brain recordings using MEG are very, very powerful, taking a naturalistic approach of just asking people to listen to an audiobook. By taking that approach, we're able to get insight into both what properties of language are present in the neural activity and the relative timing of the encoding of those properties. This gives us the ability not just to be able to reconstruct what these people are listening to, but also say which aspects of what they're listening to are encoded more robustly than others. And what's critical is that the models that we're using here actually fit on an individualized basis. So it means that we can get a decoding image like what I just showed you for each person separately in order to be able to get insight into differences in how people might be processing the same auditory stimulus in different ways. And this is, as I mentioned, this is work which lays the foundation for work which I'm currently conducting with Alex Woolgar at the University of Cambridge, where we're planning on applying exactly the analyses and experimental protocols that I described in non-speaking autistic individuals to see whether we can get insight into what properties of language are encoded while these people are listening to stories, see whether there are different types of processing strategies for different people, and then with the ultimate goal of then being able to actually come up with targeted therapies. So if we can say that for a certain individual, it's the lower level phonetic processing which seems to be weaker, then you could target you could have a therapy which specifically targets that level of representation. So yeah, great, thank you so much. I'm looking forward to having your questions in the Q&A. Thank you.
Right. Well, thank you very much. I'm really enjoying the breadth of the presentations, and thank you very much for the organizers for inviting me. So yeah, I'm with EECS, Electrical Engineering, Computer Science, and at UC Berkeley, and Neurosciences at UCSF as an adjunct. So what I'll talk about today is a new way that I think we are ready for in terms of both diagnosing and rehabilitating lost communication function. This is not done with the ASD population in mind. It is done in a very different population, but I think the takeaways are still very relevant. So I'm hoping that that'll be the takeaway. Anyway, so in the Berkeley speech group that I had, we work on all aspects of spoken language communication, both the production and perception of it, but with a view to create more human-like AI models as well, basically computational models that are mimicking human function. And this is also towards screening and rehabilitation of speech disorders. This is not needed for this particular audience, that, communication disorders are a big part of what ails our populations, and more so in kids, but also in adults. We are currently working on a project. I'll not talk about this, but this is just a teaser for what we're working on in terms of creating digital ways of objectively measuring speech function. All right, so here is a sound.
My grandfather. All my grandfather.
And basically, current AI is not great to characterize that, because it's too good to be useful. Whereas we really care to document everything that's happening, where there is a missing phoneme or a substitution of a sound or something. And we are currently using this for aphasia and dyslexia, and more in mind. But also the talks earlier in the day suggest that we need both behavioral and neurological biomarkers, and this could be a valid, a potential strategy towards that as well. Anyway, yeah, I'll not do this because I want to get to the neural side of things. But what you see here, let's see if I can play this again. Okay, this has got to work because I have lots of audio. All right, okay, I'll play this again.
12 buttons missing.
Okay, this is a dyslexic kid. He says he has several buttons missing. He doesn't say several correctly. And with our AI-based approach, I'm saying AI-based very cavalierly, but really design very precise algorithms to detect what's wrong in someone's production. So several, for example, was pronounced as swell well, and that's what we've identified digitally. Like it's for people who have gone to a speech and language pathologist, you would understand what a difficult task it is to really assess someone's language. So to be able to objectively do this is very, very useful. And the idea is to do this for all K to 3 kids by 2025, actually. And we are hoping to do that for language screening. Anyway, back to back to the talk of the day, where I want to talk about, can we create neural interfaces to decode language directly from the brain? And kind of the motivation for this comes from how laborious and erroneous current assistive solutions are for someone with stroke. I mean, I'm talking about this population, the stroke population here, but I know there is other interests here. But someone without the ability to express themselves it's a real loss in quality of life, and any improvement we can make in their communication device would really be a meaningful change. So what you see here is one of our first participants in a clinical trial. He had a car accident and he has a brainstem injury, so he is unable to speak or move the rest of his body, but he still has some residual neck function. So he has this baseball cap with a stick on it, and he pecks on the screen, stringing together letters to create a speech from what he wants to say. And as you can see, where we are, I'm really at this 120 to 150 words per minute right now, but yeah, the assistive devices really get you in the 2 digits, very small 2 digits. So the idea that Edward Chang, my postdoc advisor, and I had 10 years ago, like 2013 maybe, was wouldn't it be nice if we can decode from a paralyzed person's brain to enable them to communicate again? And that seemed like a very formidable thing, but a worthwhile pursuit. So Dr. Chang pioneered in the use of electrocorticography, where we place this grid of electrodes on the surface of the cortex, and we measure the raw voltage of what's happening on the cortex. So nothing's inserted into this cortical tissue, but sitting right on and listening to the voltage. And that's what you're seeing here in terms of the high gamma activity, which is like this energy band between 70 and 150 hertz, which is very correlated with multi-unit spiking activity. And what you see here is a perception thing. The sound size played, and you can see in that particular electrode that the red is pointing to that there is a very strong, reliable signal about like 50 milliseconds right after the onset of the sound. So this is just to show the efficacy of using electrocartography as a modality here. And in 2013 was the first time that we used electrocartography in someone, in a neurotypical speaker. They have epilepsy, that's why they have the implant, but otherwise their language function is very much intact. So this is the first time that they revealed a vocal tract map within the sensory motor cortex, which was very telling. And you can see the lips and the jaw and the tongue basically showing up on the ventral sensory motor cortex. When I joined Dr. Chang's lab, we started this, the same strategy for fluent speech production. So we had participants speak fluent sentences, and we were trying to see what each electrode was doing. So what you see here are 3 electrodes marked in A, B, and C on the cortex, and A is responsible for sounds that involve the lips closing, and B is the tongue tip touching the roof of the upper incisor, and C is the back of the tongue, which is really more extrapolation of what was shown in the 2013 paper, but this is how fluent speech is strung together. So we kind of have this inventory of space-time movement motifs that we string together in speaking fluently. And that's what our data revealed from the grids that we implanted. And this was all on able speakers otherwise. So in 2019 was the first time that we actually took it a little further and asked, can we now that we know what this part of the brain is doing, can we directly decode from the brain? So these people who have this brainstem injury, so this subject does not, but the idea is if we can directly decode from the brain, we can bypass the broken pathways, so we can externally rehabilitate them again. Right, so this was the first time that we were able to achieve, like what you see on the top panel here is what the participant actually said, a couple of sentences, and what you see on the bottom is the reconstruction of what was actually generated computationally. And the approach is very much biomimetic in that we were taking the brain activity, we were decoding these motor traces, the kinematic trajectories, like what the lips are doing, what the tongue is doing, and we have an articulatory synthesizer that then creates the sound from these movements. So this was kind of the proof of principle that we needed to start a clinical trial, which we started in UCSF, where the idea is to do this in a participant who is paralyzed on the brainstem or something more downstream, but cortically very intact. So we implanted this grid right on that part of the sensory motor cortex where I've shown a speech motor function. This was done on a paralyzed patient. And we kind of, we did this. The first thing we built was a limited vocabulary decoder where the subject was saying things like alpha, bravo, Charlie, delta. So it's like 26 codes. And then he was using it as a speller to create a communication system. And we were, of course, using like language modeling to improve these corrections and making the proper sentences. But this was the first time that we were able to do this as a speller. And of course, speech is not just the text, the words, but how we say it. So more recently, we started a speech decoding effort as well. And what we published in 2023 was this multimodal decoding approach. So we went from brain activity to essentially discrete speech units, which were coming from our computational algorithms that can compose speech. But we are also using the machine learning to create brain to sequence, and then we have sequence to speech methods. Interestingly, what we did in this participant was she was She had a brainstem injury, not injury, a stroke, and she lost her voice for the last 20 years. And but we had this grainy video from her wedding, and we kind of restored that audio, and then we used it as a digital voice that sounded like her. And the idea is, after the brain decoding happens, it sounds like her again. So that was our approach to do speech decoding. We also did this expression decoding so that she could express herself facially. So what you see here are these maps. I'll show the performance of the decoding in a bit, but I just want to show that we were also very lucky in getting very good expression decoding. As you can see, the expressions as defined by facial gestures that convey smile or a frown or happy and so on. So you can see that we have a very clean confusion matrices, meaning we can decode very high accuracy. So this is an example of what this study has done. And so what you see here is the participant. I hope the audio plays now. So you can see that, I'll pause it here. There is another video I'll want to use, but so as you can see, we have the pedestal here, which is directly reading out of her motor cortex, and we have the decoding algorithm that decodes both the speech that you're hearing in the voice that she had before her injury. Also, the facial avatar is moving with respect to her intent as well. All right, so I'll try and move on to the next slide because I have another that I wanted to show. So if you have noticed, it was quite a time before there was a go queue and then the speech was coming out. So we have since worked on something that is more streaming. So this is work under review right now. Now I need the sound.
What you say? I never.
So I hope you can see that the latency is much lower now. It's like 1 second latency. She's not vocalizing. She's attempting to vocalize. Okay, it's not completely imagined. She's attempting to vocalize, though it may not show up on her face. And that's what we're decoding. And this is work done by my excellent grad students, Kayla and Choljan. So that's the kind of the end of the brain-computer interface story here. And of course, we know that speech is not just articulation. As we just heard from Dr. Gwilliams, we have an entire hierarchy of linguistic representations. And particularly for this population in ASD, we cannot have an invasive implant. I mean, no one would approve that. Even the IRB would not approve that. And neither should we do that. Because there are too many unknowns, right? We do not even know where to put an implant. That's the biggest question. So we started a more on non-invasive. Right now, it's just control on a pilot, healthy neurotypical populations. And this is my collaborator, Jack Galland. And we started the fMRI study where participants were speaking stories, 10 minutes long stories, like they prepared, like I'll talk about my 10th birthday or something, and then they would speak. So that's the task. And so 12 stories like that, 10 minutes each, and events and so on. So the participant would come prepared, and we now have the task of understanding what's the progression of going from the idea of saying this thing to actually saying it. Just the inverse of what we've heard from Laura. So as you can see, there are several distinct representations. In the perception, you're going from audio to semantics. In production, you're going from semantics down to audio, right? So, so we have all these representations, the audio represented with spectrotemporal features, articulation represented by movement of tongues and lips and so on, and syllables. Like we've done all this innovation of very highly, robustly estimating articulation or syllabic embeddings directly from speech. And these are all the features that will go into our encoding studies. And of course, word embeddings, we have quite a few candidates to doing that. So the first thing we did was encoding the brain. So can we use all of these features to understand what the brain is doing, right? That's a very first step, first order question. And this is, just to orient you, these are maps of, so what you see here are blood oxidation levels. And you see the brightness is how well you can estimate what this part of the brain is doing from all of the features that we have seen, the lexical, the articulatory, the semantic, and so on. And these maps are really flattened out versions of the cortex. So what you see here are the auditory cortex, the sensory motor cortex, VSMC, the Broca's area. These are all implicated in speech production generally. So you can see that. But what you can see is like speech production is very diffuse, right? It is like all over the place. Which has already been documented before, but it's interesting to see that again. But more importantly, what we wanted to see was, do we have the sensitivity that we have from invasive recordings from non-invasive fMRI-like study? And indeed we do. What we see showing here is the VSMC, the sensory motor cortex, has this map. The articulatory features of the full feature set are actually encoded in the motor cortex, which is reassuring. And it also has representations that are similar to what we've seen in the invasive setup with electrocorticography. And the region of the lexical and the semantic models, meaning the syllabic embeddings and the word embeddings, are in the temporoparietal junction, which is also very interesting. While we see the entire cortex being activated, we can see distinct regions that are more syllabic and some that are more lexical, and we've seen the articulatory as well. So we kind of believe we have a modality that we can trust to understand the implicated neural substrates during speech production. And a possible hub for coordinating speech production, we believe, are the precuneus, which is like the medial temporoparietal, where you can have this interface between phonology and actual articulation. So for ASD populations, I think it is interesting to see where along this progression they are, like which kind of features are better represented, and then having decoding attempts, if we create them, that target on that particular representation that is still intact in these folks. Anyway, so there is a bunch of ideas that I'll talk about, but I think I ran out of time, so I'll end here and open up for questions along with Dr. Gwilliams. Thank you.
Thank you both. That was both very excellent presentations. I have one question for you, Laura. When you're mapping neural signals across that full hierarchy of different elements to be encoded, do you have a way of identifying which part of the brain that neural signal is getting processed?
Yeah, that's one of the challenges with this non-invasive approach. And so the power of the approach is that we can pull out signals that are very, very tiny. So they account for a fraction of a % of the actual signal that we're measuring. But it means that we can't very accurately determine where those signals are coming from. We can do a fairly good job with, like, the closer you are to the actual speech signal, so the speech sounds, we can reconstruct where those are because they account for a higher percentage of the signal that we're recording from. But as we go more and more abstract, the signal strength becomes weaker, and correspondingly our ability to say where that signal's coming from. Yeah.
Okay, thanks. Yeah, I just saw this recent paper in Nature by Gwilliams of MIT where he's talked about the prefrontal cortex, for example, only working on semantics but not looking at sounds at all. So what other studies, could you map such findings eventually on your data to say, well, most likely if this person in this individual, semantics is kind of where the problem is, that most likely the prefrontal cortex is affected?
Yeah, I think that there's definitely ways of being able to identify where the signal's coming from. You just need a slightly different experimental approach than what I'm taking. All right, thanks.
Thank you.
A great presentation for both of you. I have a question for each of you. For Laura, speech perception. I want to have your feedback about the autistic individuals. So often we feel that the challenge that they have is like somebody who wants to speak a foreign language.
Sorry, say that sentence again.
The challenge that we feel in the kids with autism is that they hear or they express themselves in a way that if I want to speak a foreign language, is not something that is my maternal language. So the feeling comes like that. Do you have any comment in regard of, is it because they don't have that hierarchy that you mentioned? Because the hierarchy that you mentioned is for neurotypical individuals, but maybe for autistic individuals, this hierarchy doesn't work because they are really hearing and expressing themselves like they are talking a foreign language.
So I think that is essentially one of the questions we can address with this approach. So if, say, I am listening to a language that I don't understand and you recorded my brain activity, you'd be able to decode just fine the lower level properties. But then as soon as you get to the words and above, it wouldn't be present. And so that's one hypothesis. For some individuals, maybe that is what the brain activity looks like, but maybe not for other individuals.
And for the speech expression talk, many of individuals on the spectrum have the difficulty of to start the speech. So if you give them the initial part of the speech, they can do the sentence. So probably the prefrontal area that is having the problem. Do you want to expand on that based on your work?
Yeah, I mean, so that's exactly, I think, again, would be interesting to see where the differences are against like typical controls. Because in neurotypical individuals, we see a marked trajectory of the premotor, the Broca's area lighting up before the motor cortex actually takes on. And from the fMRI study, we've seen like other areas also being included, largely before the articulation itself. So having a problem just starting might indicate that there might be something might be happening in the Broca's and the premotor cortices that would be interesting to just document in these individuals, and then think about how to deal with that. But just as a biomarker, we need a biomarker. Like that would be nice to see. That what you expressed is a behavioral biomarker, but relating it to a neural underpinning would be nice.
What are your thoughts about the fact that a lot of kids, even though they cannot communicate in full conversational speech, but they have very good echolalia, great scripting, and even musically, when it's music, song, they can learn it in listening twice, they can sing the whole song. So isn't it more an issue of word interpretation than actually the being able to use the words and repeat the things?
Yeah, so I think that there are a number of different facets to it, it's interesting the examples that you give, because there are also, like, for people who stutter, for example, there's also, like, they do just fine with being able to, like, repeat with a rhythm or like with song. So there's clearly a number of like interconnecting components. But I think that in the receptive language case, at least, I think that it would be also helpful to see whether this kind of receptive language fingerprint maybe is also different for people who are facilitated by these types of strategies or not, and that might also help us to understand which networks are involved for different people.
Is an interesting thing for us to think about in terms of like what tasks to run. Is like we should think about things that are implicating the working memory system, not so much the language production itself. So we should have like pseudo-syllables and tasks with varying levels of linguistic ability, but also other working memory like functionalities that might still be intact or so. Yeah.
Yeah, I had a comment that, during the course of the conference, I think it might have been clear that many of our kids have a relapsing remitting and a non-standard physical ailments as well. And according to that, their functioning level also goes up and down. So whatever you design in terms of data collection or experiments, I think you should have like a questionnaire about their current health status and work with the parent in terms of taking the data when they are able to do it. Otherwise, it might screw your data collection.
Yeah, I think parents and caregivers are the people who know the person the most. So
yeah.
And I think there should be like a behavioral assessment to calibrate where they are on the day, maybe.
Yeah, and also like somebody mentioned, a questionnaire could also determine what fundamental problems this person has that might affect your experiment. For example, if initiation is a problem, that person may have initiation problem in other things too. So it's across the board, so it doesn't reflect on.
Yeah, absolutely.
So I'm thinking that it would be ideal to use this as a biomarker. In fact, every day, like if my son has an app, for 5 minutes, do some quick assessment. Yeah. So I know how his brain is functioning on that day. Like I can track his ups and downs. So it's like a biomarker.
Yeah, absolutely. I think we need a behavioral biomarker that sets up the day.
Yeah, this question is about expressive language, and in particular, it's about letter borders. So now there's an increasing number of my patients and my son who are using a letterboard to communicate. And in some cases, it can advance a student as much as 5 or 6 school years in 18 months. So it's incredibly powerful. And what it points to is difficulties that our instruments have in measuring IQ, intelligence, working memory. And I guess my question to you is, what accommodations do you think you're going to have to make in your research design to accommodate people eventually who use letterboards for expressive research? Because they are having to attend to an additional technology.
I can only speculate. I've not worked with this population, but so I think that's where I said what I said about we should be careful about the task design, and we should adapt to their current modality of communication, and reinterpret all of our tasks in the light of that modality of communication. And not measure everyone by the same yardstick. I don't think that's appropriate.
Yeah, hi, I have another question. So everything you described in terms of helping that lady be able to develop or be able to produce speech, including the emotion on the face, that was really fantastic. And I was wondering, how far are we away, even from a research perspective, not from a productizing perspective, but research, taking, say, somebody like my son who has zero speech. He used to speak, and then he regressed, and he has no speech now. To be able to say, okay, in these various levels, the brain level, and within the brain, all this level, and then down to the physical level, where the breakdown is occurring for that individual, how far are we from being able to, research or study something like that?
I think we are very far. I think that's why the Brain Foundation and all these Catalyst experiments are really to ask these questions. Even in health, like controls, we do not have good models of here is exactly what's happening through speech product. Like there's still areas we do not know that are involved in the exact trajectory of how things go. But that's a multidisciplinary problem. Like we need linguists, we need psychologists, we need engineers, we need like neuroscientists and so on. So I think forums like this are important to enable those collaborations and those experiments. So I think technically there is nothing stopping us to doing that. It's just, everyone is siloed, that we are not addressing those fundamental questions, as you say. Yeah.
So the problem is not scientific or technical, it's structural in terms of how research is organized. Is that what you're saying?
Yeah, to address the specific question of like, what is happening in someone like that? Like, we do not have like an imaging protocol that exactly tells you where they are, what is intact, what's not. Like, that doesn't exist. Just because I think people, if we all put our brains together, we can come up with some tasks to understand what's still not typical about their expressive or receptive language.
Yeah. So I was very intrigued because we have had some studies done with now something like leucovorin, and Dr. Fry is sitting here, and he could speak on that, but where there, at a biological level, it has helped some children produce speech. So I'm just wondering if, your work in understanding how speech production happens with the changes that leucovorin might be bringing at a brain level, combining those two might be interesting to observe.
Exactly. That's what Pramila was saying about a biomarker, to see if there is an improvement with respect to these interventions. And that can be visually, both behaviorally and neurally be documented. That would be excellent. Yeah.
Okay, thanks.
So in my son's case, the speech therapist has helped quite a bit, but still we struggle in trying to get the comprehension, get going with him. He can read, he can utter words, he can even respond to one-line questions, but conversation doesn't happen after that. So I wonder if you have any insight into any other higher order centers that could be playing an essential role in this form of communication.
Yeah, so I didn't quite get the last sentence that you said. Can you say just the very last part again?
So the question is, the speech therapist has helped to get few words out of my kids, language abilities, but it doesn't translate to conversational skills. So if you ask a question, there is an answer to that question with one word, but it doesn't go beyond word. There is no reciprocative communication that's going on. Although we see that, he is very excited to express everything that he wants to express, but the words does not get out from him. So that's, part one. Part two is, he's able to use all the words when he reads, but when it comes to comprehension, he is not able to bring connection between one sentence to the other sentence. So it's kind of like that connectivity is missing. So my question is, is there anything that you have insight into what other higher order centers of the brain could be operating, in mediating and modulating this particular function?
Yeah, so I think that I could definitely imagine doing something like the experiment I described in this case, where we already have a idea of which levels are breaking down. It would be the longer time scale contextual information, but it might be possible to actually give a more kind of concrete answer as to precisely which level gets disrupted, and perhaps over what time scale gets disrupted. Maybe information is processed fine. Maybe it's not about abstraction. Maybe it's about time scale, which from a behavioral perspective is hard to disentangle because they tend to go together. But from a neural perspective, you could actually disentangle the two. And then maybe it would be possible to actually, develop therapies that actually are getting at the core of the issue. Maybe things are slightly, misdirected, and knowing where to direct them would help.
Yeah, just also, that's an important point. What you're bringing up is the interaction between perception and production, right? That again, I think, is a systemic thing. Like we, for example, Laura exclusively largely works on perception, I work on production. So I think we need a task that jointly, tied together, that's grounding both the perceptual and production signals in a conversational style to see what neurotypical conversation trajectory is and what's happening in someone who is not as expressive, comprehending. It's exciting to just listen to all your perspectives because it's giving ideas, but we should, yeah, that's what I think the best outcome.
So, talking about all this, one thought comes to my mind, and this is very true with my daughter, who is very vocal. She can build sentences, but, to the comprehension part, if you give a pause, let her process, so there's a time gap, and then after that, she's able to actually pretty much have at least, I would say, for a minute or so, a reciprocal conversation. So there is this time delay for sure. So if you give her enough time, then she's able to do it. So, just a comment.
Yeah, this is, I'm sorry, just to add, I think that this is really helpful feedback as well for designing experiments, not just with, my prior literature in mind, but actually by, being engaged in conversations like this, that we can, be open to different types of, hypotheses. Thanks.
So my son's articulation skills is kind of a combination of what this gentleman and she pointed out. So it's like it's limited, and often his responses are just yes or no, and most of the time it's yes, So, but then he's not able to. You can see the frustration in him. He wants to say something, but he's not able to make a full sentence out of that. And sometimes, as she pointed out, so sometimes, I ask him a question, and then after 20 minutes, he comes back with a response. So it's also delayed response is also fairly common. And we've been trying very hard to broaden his vocabulary so that he can at least say what's on his mind. So it's clear that he wants to say something, but he's not able to express it. So the articulation is one of the biggest challenges for us. And so anything that we could that could be done to fix those problems would be fabulous.
Yeah, and on that point, also building on what Gopala said, I think it's also gauging comprehension can also be really difficult, because usually the way we do it is by looking at the person's production. And so I'm hoping that, at least with the project that I proposed, we can actually get a measure of comprehension without having to rely on any sort of production at all. And then we can build in the production part.
What about languages that are different, follow a different structure? Do you have to maybe it's the wrong word, pre-program the system to match a different language structure in order to be able to decode that? And then extending on that, would people with autism, would you treat it as a different language, or would you treat it as whatever their native language is, and then try to decode that?
Yeah, thanks. So the features that I described are common across all languages. The only difference would be what features tend to occur in what orders, for example. So, English likes to put adjectives before nouns, and in French it would be noun adjective. But that is not an issue from the modeling perspective, as long as the annotation is correct and temporally aligns. And that's also the beauty of language, I feel, as well, is that they seem very different on the surface, but actually structurally languages are very similar. And to your second question, we would use the same ground truth language for both the control participants and the ASD participants.
Also, I know people who can't speak may be good at the comprehension and the other way around. So, from the results, like, what is the difference in the processing time for the comprehension? I guess time of the first presentation.
So the difference in processing time between control participants and participants with autism, or just across the different levels of representation?
No, like, yeah, with autism, and also speech impediment or speech impairment is a variable.
Yeah, I haven't looked at that myself, but I think that there would be differences in the timing, and you might find that the hierarchy that gets built is ultimately the same. The only difference is it takes more or less time to build it, and that would be my hypothesis for a number of different cases.
When we discuss this issue of the processing, in the audiology field, the processing problem, we call that central auditory processing disorders. If something is well defined, we can evaluate that, we can diagnose that, and we know what are the treatments for that, etc. Like fast forward, etc. My feeling is that what was mentioned a few minutes ago is the distinction between speech and language. Actually, the school system does that very well. They say, oh, your kid doesn't need a speech therapy, doesn't need a language therapy. And I think language is a level higher, as he mentioned a few minutes ago, is the level of comprehension processing disorders. So, and I think, unfortunately, I never heard about those entities the same way that we talk about auditory processing disorders. There's also entity that we can call comprehensive processing disorders, and also the same way expressive language processing disorders. That some people call apraxia of speech, but it's not well defined, because as soon as they talk about apraxia of speech, they think about what was shown before, that there is area in the brain that doesn't connect well to the tongue or the lip. But that's not the case. The problem is the processing disorder of the expressive language. That's a motor issue. And I think in your study, if you can define better this apraxia of speech, that is different than the apraxia of speech that's used by speech therapists, because that's something different. That's an apraxia of the expression of the language, then you're going to help a lot of field, because this is not well defined. The same way that now we understand and we evaluate auditory processing disorder, you need to define what is the expressive language processing disorder.
I agree completely. So I think one of the things to look forward to, I think, in the future is creating neurosensing modalities that meet the person where they are, and then rest should be computationally or post hoc compensated for and digitally augmented. That way, expressive language, maybe it can kickstart the conversation for them, and then they can take it from there, or whatever else their condition is. Yeah.
Can I add one more? I think you could take it as a clear reflection of how great your work is, both of you, that you've had so many questions, and I'm sure we're running way over, but it is really a reflection of how amazing the work is. The only thing I would suggest is really trying to combine what you're both doing with surface EEG, because both MEG and invasive recordings are not easy to come by, nor are they really practical for large volumes of patients. Where surface EEG is, the problem obviously is, with surface EEG is it's almost like a far field potential by the time you're seeing it, right? You're not going to get the same robust data. However, if you can correlate what you're measuring on MEG or corticography with a surface marker, then you have something. And And I think what we need clinically is sometimes we just need a very simple binary question of, is comprehension intact here? And that would help a clinician move forward in a non-speaker. So that's just a suggestion to think about.
Yeah, thanks for that. And actually, the project that we just had funded by the Brain Foundation is planning on primarily using scalp EEG, also because it's more accessible to the population too. So yeah, that is the plan. The point's well taken. Thank you.
Hi, I'm Zenzi, and I'm a 55-year-old autistic person who had no developmental signs. In my 40s, I lost nearly 90% of my capacity to walk and talk. I've got hundreds of YouTube videos of me trying to regain the capacity to speak and to talk. And just last week, somebody came and smoked behind my vehicle, and I got out to say, please move away. I became enraged, and the words were all correct. They were in an entirely wrong order. So if there's any way I can offer my N+1, I'm here in the Monterey Bay area to start designing some trials, because I can, on demand, experimentally increase my autism. And right now, again, I can hear my voice at some of the earlier presentations. It feels like what somebody might say, I'm anxious, but I'm not. It's that literally the stress of my vocal cord, when I'm hearing the feedback come through here, I don't have a way to time what I'm hearing, all the amplification, and it's causing my vocal cords to literally constrict and want to stop talking and be very, I'm angry that they're not working, and that becomes a constant feedback loop, that you just stop talking because it's so difficult and it feels physically impossible to talk. So if there's any way I can help, let me know.
Thank you for the comment. I think this also talks back to Pramila's suggestion that we should work with, the condition that the person is in, and then design our experiments around that.
So I think, thank you so much. That was such a great session.